Oh boy, okay, we're back. My name is Michael. I'm a goat farmer from the other side of the Continental Divide, and now we're going to talk about some coarse graph theory, which is different from graph theory, as this is beautifully demonstrated by this professional graphic. Here we have a graph, and it's very, very far away. So far away that we have to use a magnifying glass, don't ask, in order to get a good look at it really close up and actually see what's going on with the graph. That is the last we'll ever see of the magnifying glass, because generally the motto of coarse graph theory is don't sweat the small stuff, and it's all small stuff unless it's not. And when it's not, it's big, like really big. Okay, but we're going to start very, very basic. Like you guys saw I guess I have this. I'm getting ahead of myself. We have a roadmap. Okay, coarse graph theory, what we try to do, the idea is to take graphs and look at the big picture. What's going on? We say we study them at scale. Small, finite, they go away. We do not care. If it's finite, it's gone. We're not going to worry about it anymore. Sounds good? I want to approach this talk in a slightly different way than I've done introductions to coarse graph theory before, and that's mostly because of the graph theory word in there sometimes is a little misleading to people. One of the big, most important questions you do in graph theory is you look at the differences between squares, triangles, and circles. What do you notice about those three things? Different number of dots. How many dots are in each one? What do those numbers have in common? They are all finite. And so as far as I am concerned, these are the same picture. Okay? Good? Good. Now we can get to the basics, the very most basics. Ignore this slide. We've already done this. Take us to the next slide. Okay. We're going to focus, instead of on the graph theory part, we're going to focus on the geometry part, and then build that into coarse geometry, and then build that into coarse graph theory. So geometry, we're going to start with a really basic idea, area. Jump us to the next one. Did everybody read the definition of area? I just want to make sure that we're all clear on this. Question 1. Find the area of this figure, which is a square. Hold on a second. And it says 1 by 1. You know, that's just an arbitrary unit. We don't really care what 1 is, right? So I'm just going to call that a 1 by 1 square. And this is what I mean by blowing the QED count just out of the water. Is, you know, several of you actually just took this for granted, that the area of a rectangle was its width times its height. No, we prove things like that. Okay. How? How in the world am I supposed to prove this? Would you jump me back to the definition real quick? What tools do we possibly have access to that we could use to think about how many 1 by 1 squares I can fit inside of this 1 by 1 square? We have 1 by 1 squares. Beautiful. Okay, now how many of them can I get inside of there? At least 1. I can definitely get 1 in there. But remember, we want the maximum number that I can put in there without overlapping them. So what am I going to need in order to see if I can't make sure I can't get any more inside of there? Exactly. I'm going to need another square. And now we can look at this and we can go, yeah, I can get 1 square in there. No, there is no way. I can get exactly 1 square inside of there. And so you can jump us forward one more slide. The area of that 1 by 1 square is 1. QED. Okay, now you can take us one step forward. This is different. This is strange. This is not a square. We now have a 2 by 1/2 figure. Oh goodness. Anybody have any idea how we can figure out what's going to go on in a 2 by 1/2 figure when all I have is 1 by 1 squares? Yeah, I distinctly remember something in that definition about cutting, tearing, maiming, and deranging my squares. Squares are not people. We can do to them whatever we want. Now, I really hope this works, because one of the beautiful things about mathematics is you make a mistake, you crumple up the paper, you throw it away, and you start over. I only get one shot at this. I don't have that many squares, okay? Yes, I did cheat by pre-creasing it. Ha, look at that. How many of these? This is still one square, right? One square. I can put 1 in there. I can put 2 in there. That's it. That's all I got. Okay, so what is the area of that thing? Still 1, QED. Jump me forward one more, if you would. Can you give me one more slide?
More or less?
That looks about perfect. Now we have this other square. It's got some weird dimensions. It starts with, what is it? It's got 2, so same height, but then we add an extra bit coming off of it, something like that. Okay, well, we know how to play this game, right? We already know this chunk. I can put my 2 halves inside of there. And then I ran out of cardboard, so we can just put 2 of these squares over here. That looks pretty good to me, right? What's the area of that figure going to be? I put 1 square in there, then the 2 halves, and then the whole one. How many squares is that? 3 squares, QED. Hey, come on. You guys all relied on this as an assumption. Give me my moment. Okay, there's one more on this page. Sure. Ooh, yeah, there it is. Now we have to get real creative. Well, what's going on here? When I split my square in half, I can just stack them up on top of each other. Now I have to split them up a little bit more than half. I got to split them up into W. Let's rely a little bit on some, instead of, cutting and tearing and maiming and deranging, let's just stretch them. Take a square, put it in there, make it shorter, and stretch it out as long as you want. Make it some nice even thing that'll split into the height and the width. I'm not going to go through a whole proof of this. We won't count it as a QED. What's the area of that rectangle?
We're afraid to say now, Michael.
Yes, good. I've traumatized you. Mission complete. Now that you have forgotten everything you knew, we can just go. The area of that thing, should be pretty clear to everyone. It's going to be the height times the width. How do we prove that? Make our 1 by 1 squares super duper tiny and start stacking them on top of each other. Blow the whole figure up, fill it up, divide them out. There you go. Mission complete. Does anybody need more of a proof than that? The answer should be yes. Too bad. We're not going to do that. You had a question?
Just before you said stretch.
Yes.
So
one of the ways to think about, putting your squares inside of here, when I say stretch, you can't change the area.
Right.
So if I make it longer, long enough to fill in my W, in order to not change the area, how did I do that? Well, I would have cut it into strips with some certain height on each strip, and then laid them out next to each other to make the width I need. And when I do that, the height is going to be reduced to what? It's going to be 1 over W, right? Yeah, I think that's right. And then you get a bunch of those, 1 over W, you'd stack them up a bunch of times. In fact, how many times would you stack them up on top of each other? H times W, because they're each 1 W thick, and you need to stack them until you get to a height of H. Area, width times height, QED.
Now you got it.
Yeah, now you guys made me work for it. Okay.
Then can you only have integer numbers for the area of a shape?
Interesting question. Jump me to the next slide if you would. Ooh. That's a little strange, isn't it? I mean, we know how to deal with, am I going to draw a picture for this? I'm going to draw a picture, but we're not going to measure it. Why? Because measuring is going to take way too much of our time, and nobody's got time for that. So we have a 1 by 1 square, but then we've attached to that something. Something that isn't quite a 1 by 1 square. Something that looks a little like that. Now, if all I had at my disposal were 1 by 1 squares, I wouldn't be able to do too much with this. Fortunately, we have the ability to do whatever we want with these 1 by 1 squares. There we go. What do these have for area? Well, they're both half of a 1 by 1 square, right? What do you think we should call their area? Can I get a half again? A little louder? Yeah, half. Half seems fair. So if this is a half and this is 1, we put them in there. Hold on, let's see. How about like that maybe? 1 and a half? 1 and a half. Okay, jump me 1 more forward. I guess we do need a QED for that, right?
No.
Okay, jump me forward 1 more. Ooh. Ooh, no, back 1, sorry. Right there. Right there. What's going on there? We still have this bit hanging off the end of our square, but it's a little different. We've got it going what? Something like that. This one shouldn't be too difficult. We've already got the pieces of our puzzle, right? This is what was formerly known as a square. Something like this, maybe? Yeah, if my drawing skills were on point, that would look way better. Okay, so what's the area of that thing? 1. Okay. Jump us forward 1 more. This thing here, it's a similar idea, but we've just exchanged our nice, clean 1 by 1 dimensions for another, what did we call them this time? Are they W and H still, or are they, yeah, W and H? We got a W going on here, we got an H going on here. I don't have props for this. We got to just think through it. This looks really close to something, right? If this piece weren't right here, if instead that piece, well, not that piece. What am I talking about? This line doesn't exist. We're looking at just this area. It's this piece that's looking a little suspicious to us. If this piece didn't live here, instead we cut it right down the middle, pick it up, bring it over here. This is still going to be W. This is still going to be H. Hey, that's something we've already seen, right? Okay. So I want to stop here for a minute and think about what we just did. We took this parallelogram, we cut part of it off, we picked it up, we moved it up to the other side of our square. Now it's something we know the area of. That area is going to be WH. But how do we know they are the same thing? Well, the reason we know they're the same thing is because if I were to take this piece of it, cut it off right here, now I have this piece that has a definite fixed area. And I'm going to pick that piece up and I'm going to move it over here and I'm going to drop it right there. The area of this piece I picked up and I moved hasn't changed. This is an idea in some fundamental education, you would have learned about as the congruence of two figures. We'll talk a bunch more about that later once I figure out if my slides are in the right order. Take us forward one. What's the area of that thing? We already did this. It's a square cut in half, 1 by 1. That's going to be half. Jump us again. We're not going to worry about these ones. Take us to the end of this. Anybody have questions about how to find the area of a triangle? Going once? Going twice? Okay. Just for the sake of it, we have a triangle going on there. Let's just do it real quick. It's the same congruence argument. We have a triangle, has some strange dimensions to it, and one of these we're just going to pick and arbitrarily call this W. Then we're going to grab a line right down the middle, well, to the farthest point from the W line. We'll call that H. And now we want to somehow use a congruence, something that doesn't change the area of a piece, to pick something up, move it around, and turn it into something we know how to deal with. What was the slide right before this one? Areas of parallelograms, right? So maybe we want to turn this into a parallelogram. So let's pick up this entire triangle, flip it right over this line, drop it up there. We're going to get something that looks like this. Okay, now this thing and this thing, they are identical copies of each other. So they're going to have the same area. And the area of the entire thing, well, this distance is still W. This distance is still H. That's going to be WH. So if I took away this copy, what do I have? Half WH. Okay. I promise we'll get through this real quick. Take us to the next one. Oh, I needed something about pi, right? Little known fact about pi. Also possibly just made up on the spot fact about pi. You know why it's pi? Right, the area of a circle, if I have a circle here, the area of that circle is the radius squared times pi, pi r squared. Actually, it's, if we make this radius 1, then what's the area of that circle? Radius squared is 1 pi, area is just pi. That's something we know, or have supposedly been taught at some point. We'll get there. So the reason that pi is what it is so that it's actually the area of your pies. All those pies we have out there, they have area pi. Okay, dumb jokes aside, they all have radii of one of their radii, and so they have area of one of their pies, obviously. Okay, so pi jokes aside, I needed to do something about pi. The problem, we want to approximate the area of this circle using what we've learned. Well, I don't know how to make the area of this thing, but I can approximate it, right? If I just break it up into some triangles. If this thing has radius 1, what are these triangles' area? 1, 1, 1, 1. They're all going to be 1/2. Add them all together, you're going to get 2. I took physics 1 from an astrophysicist. We regularly assumed pi was 10. Okay. With that out of the way, pi is approximately 2. For the purposes of this talk, we can assume y. Pop quiz.
They're both small, so basically both.
They are both finite. Okay. Now,
3 pi counts, by the way.
okay. Does it bother you that I didn't make a full
No,
box?
you did root 2. Okay.
Okay. Now, we have another fun definition here. This idea we talked about, congruence, picking things up, moving them around without changing their area. we're going to deal with that same idea under a different name. We call it an isometry. Iso for the same and metry for distance, something that keeps distances exactly the same. So just a very general example. This here is a triangle. Let's pick 2 points on them. Let's very creatively call them P1 and P2. And now let's pick this triangle up. Let's move it over here. Let's spin it in a little circle. Did the distance between P1 and P2 change? No. Very intuitively, that's the idea behind an isometry. It's something that doesn't change your distance between points. Okay, problem. We want to prove that 2 shapes are isometric if and only if they can be placed exactly on top of each other. Well, it just so happens I have 2 shapes right here that can be placed exactly on top of each other. So the only remaining question is, what does it mean for them to be isometric? If an isometry is something that keeps distances the same, 2 shapes are going to be isometric if I can use an isometry to turn one of them into the other. Let's see, what exactly do we want to prove here? Let's put one triangle here, let's put one triangle here. The isometry I want to use is to move one of them right on top of the other. This is an if and only if statement, so I need to prove 2 things. One, I need to prove if they're the same, I need to build an isometry that moves one on top of the other. And 2, if I have an isometry that moves one on top, if I have an isometry, I need to prove that I can put one on top of the other. One of these is easy. One of these we've already done. If these 2 shapes are the same, pick one up, put it on top of the other. That's an isometry. They are now on top of each other. Mission complete. Okay. The other is a little bit harder, but not much harder. It's still pretty straightforward. If I have 2 shapes, and let's imagine that there is not an isometry between them. So we're going to go for contradiction here. That means that there is some pair of distances I can't duplicate. There's some point P1 here and some other point P2 over here, such that no matter how I go through mapping between these 2 figures, I have to break this distance. It has to change. Well, the only way that I can have that point go to somewhere that I can't make the same distance is if it's not inside of this. I'm doing a bad job of explaining this. Do you guys feel like you're comfortable with this idea, or do you want more information? Okay, we'll take it, and we'll just roll with it. Jump me forward. Okay, now we get something a little bit more interesting. This is, rather than resembling grade school mathematics, this is probably looking a little bit more like something you would have seen in middle school, maybe high school. A little bit more interesting. We have 2 triangles that have exactly the same side lengths. So there's a side that is exactly the same length as another side. There's another side, which is exactly the same length as another side. And the third side is the same length as the third side. We want to show that these 2 triangles are isometric. That means we want to build an isometry, something that keeps all the distances between them the same, when I pick a random point out of this triangle, and I take it and I drop it over here somewhere. The key recognition, the key idea behind this is that we don't really have to talk about, building a function that takes every single point here to a point over here is kind of a little difficult. So we only have to take a couple of very important points, and then everything else is going to just follow from that. You guys have ever heard of the idea of triangulation before? The idea is that if I have 3 circles, I pick a point, pick 3 other points, these distances uniquely determine that point. This is the only point that is this distance from this point, this distance, or this distance from this point, and this distance from this point. That's the idea. this point is uniquely determined by its distance from this point, and this point. And so if I figure out where this point, and this point goes, and I know it's an isometry, well, where this point goes is uniquely determined, right? So just off the top of your head, where do you think this point, and this point should go? If this has side length, let's call it S1, S2, and S3, then S1, S2, and S3. Then we could label these points. Maybe this point is going to be, it's the intersection of S1 and 3. This one here, we could call it it's S2 and 3. And this one we could call it is S1 and 2. Well, it seems like it's a fair assumption. This point has to be the same distance from this point, so they probably should be separated by that edge. Let's take this point. Let's put it right here. Let's take this point. Let's put it right here. Let's take this point. Let's put it right there. Okay. Now pick any point inside of the triangle. Well, I don't know exactly where it goes, but I know this distance, and this distance, and so I can find exactly one point over here that it's going to go to. Great. I'm calling that good enough. We have that two triangles with the same side lengths. We got an isometry. Go.
So this triangle, the way you draw it, it kind of like forced the mapping.
Exactly.
Right? If the triangle was like isosceles or something, you might have some options, right?
If the triangle were isosceles, you would have some options, but as soon as you have to fix 3 points, and then you fixed everything.
I mean, I
Right.
think that the distance would still be.
Right. You do get some options there. In fact, you would have exactly 2. Here, this triangle is kind of weird. We have only one choice for this isometry. If it were an isosceles, one of those points is unique. The other 2 are similar. They can go either way. You're going to have 2 different isometries taken one to the
That
other.
actually gets the hard.
Yeah.
There's potentially multiple isometries.
Yes.
So would it then be accurate to say that an isosceles triangle is isometric to itself?
It would totally be accurate to say that an isosceles triangle is isometric to itself, but you can do even better than that. I mean, here's a question I'll turn that around and ask you a question. Interview tactics. Is it fair to say that a triangle, even if it's not isosceles, is isometric to itself? The
Yeah,
answer is yes.
Interesting isometry that's not the identity.
Yeah.
Right.
So we're not requiring a non-identity function. Something is going to be isometric to itself because taking every point to itself is an isometry. Okay. Jump me forward again if you would. Okay. I've done all this talking about isometries and distances because I want to talk about metric spaces. We're going to be talking about metric spaces for a while. In order for this notion of an isometries, we use them to study geometry. Without them, we can't do, well, you can do geometry, but it's weird and not the geometry that I want to do. So you can do a ton of geometry using isometries. Our goal is to study coarse geometry and through that study coarse graph theory. So let's take a moment to properly understand isometries. In order to have an isometry, well, it's pretty simple definition, function that preserves distances. Distances are the next point of contention. Let's talk about what it means to have a distance. Distances are defined on metric spaces, as is cleverly illustrated with this beautifully intuitive definition. A metric space is a collection of things with a notion of distance between them. I probably have an example on the next slide if I had to guess. Nope, I don't. Oh, well, that's okay. Meaningful notion of distance. Let's take it as an example, my whiteboard. This is a collection of things, right? I can put points wherever I want on this whiteboard. And there's a pretty meaningful notion of distance between them. Don't like it, ask the ruler. Okay. But that doesn't make as much sense when we're talking about less concrete things. Like this whiteboard, it's pretty easy for me to tell you what is meaningful about a notion of distance. We want to be a little bit more rigorous about that. Now here's where I abuse pauses. So you're going to have to rapid fire a couple of slides. Ready? What does it mean for a notion of distance to be meaningful? Well, we have, I think I put 4 things down here. Some people do 3, some people do more than that. I think I have 4 here. We want something, a point, a thing. How far away from itself should it be? It should be itself. It shouldn't have any distance from itself, unless it's really big, and that is an interesting question in this context, but we won't worry about that right now. Different things, if I have 2 things, well, they shouldn't be the same thing because they're not, so there should be some distance between them, and that distance had better be a positive number. What else do I got going on here? Distances must be symmetric. So going this way from point A to point B, it had better be the same distance as if I spin around and I go from point B to point A. And then another, what was it that we used earlier? You talked about it, your favorite inequality? Triangle inequality. Distances must never be shortcut by a detour. What does that mean? Well, let's just add something right down here. What do you think I should call this point? I like C, but you know what I like even more? Detour. I'm a joker. If you don't like it, the door's right there. Okay, point A.
Egregious use of the letter.
To D, and then to B. Well, that, and then that, I just took a detour. I said that can't be a shortcut, right? So doing this and then doing this had better be longer than doing that. Or equal to, if my point D were right here, that wouldn't really be a detour though, would it? Pit stop. Point P. Okay. That is, as that slide is probably titled, very informally what we mean by a metric space. Advance me one more. Problem. We got to argue that the distance measured by a ruler between points on a plane is a metric. Well, we already did that once. Like, we said it was meaningful. We just asserted that by fiat, like a ruler. Now let's do it using the ideas we already have. If I put a couple of points on a plane, let's say here, over here, down here, up here, maybe right here. Okay, so what are my conditions? First things first, if I'm trying to measure the distance from any point, let's say this one, to itself, I could do this, but what is my ruler going to tell me? What's the distance from there to there? Yeah, 0. Okay, check mark on problem number 1. I don't dare say QED. I think I'd get lynched. Okay, next, point number 2. If 2 points are different, let's say point A and point B, well, I better get a positive distance. Check. Okay. Third point, distances had better be the same going one way as going the other. Let me do a quick little isometry with my ruler here. Check. Okay, last things last, we need to not be shortcut by any detours. So let's put a point right here. Detour. Maybe just to keep everybody happy, there's C. G is going to get enough abuse later in this talk. We'll save G for now. Okay, so From A to B, what is that, metric? There we go. From A to B, 8.5. A to D, 13, 13.5. B to D, 8.5. Well, yeah, it's definitely longer to go through the detour. Check, mission complete. Something very incredibly basic that we all knew, we have just proven. Okay, take me to the next slide if you would. There we go. Now we get, you want me to QED that?
Yeah.
Okay.
I also think we should use metric on this. Just makes sense. Like.
You are actually mind blown. I hadn't even. So for the folks online, the brilliant suggestion that I just received, we really should be using the metric side of this ruler to prove it's a metric. Okay. Now, formally. Ooh. What's the difference between formal and informal? I mean, I'm here to give a fancy talk in this shirt. It's not going to be a suit and tie. I think I heard the answer in the back there. Symbols. Informal means I tell you, and if you can't dazzle them with brilliance, then you just baffle them with you know what. Formally is kind of made up by a whole bunch of people who don't like that idea, which, frankly, they're justified in it most of the time. We want to be much more rigorous about what we mean by metric space. We want to replace all of the words with symbols. And so we're going to denote the distance between 2 points in the most creative way that the collective minds of humanity could come up with in the last 1,000 years. The distance between a point x and a point y is going to be called distance of x and y. Great. Okay, so our 4 points in rapid-fire succession, if the distance from a point to itself has to be 0, well then the distance from x to x had better be 0. Okay, the distance from x to something not x has to be bigger than 0, so the distance from x to something not x had better be bigger than 0. For those of you who are truly worried about my formal example lacking quantifiers, I'm pretty sure I put them in the slide. It says that x and y are different, right? Yeah, I have distinct points x, y, and z. That means they're not the same thing. Good? Good. Okay. What else did I have? The distance going forward had better be the same as going backward. So distance going from x to y had better be the same as the distance going from y to x. And then shortcutting it with a detour, distance from x to y had better be shorter than, or possibly equal to, the distance from x to z plus the distance from z to y. Okay, and now we've actually justified the triangle inequality. That is what we call this. Why do we call it the triangle inequality? Because it's the distance from x to y, and it had better be longer than the distance from x to z to y. It comes from a triangle. Neat. Okay. Take me to the next one, if you would. Formal example. Finally, we're getting to some real math. Okay. We want to prove, I mean, this talk isn't, I'm talking about a whole bunch of geometry, right? But it's titled Coarse Graph Theory. Let's get some graphs in the picture. We want to prove that graphs have a meaningful notion of distance, i.e. we can look at them as a metric space. So I put that little observation, a graph is a set of vertices and edges, because I didn't quite have it hammered into my head yet that there was going to be not 1, not 2, but 3 talks on graph theory before this. Nevertheless, review never hurt anyone. I shouldn't say that. Maybe it did. Okay. A graph is going to be a set of points. We call them the vertices. There's going to be edges going between them. And we're going to call those, very creatively, the edges. Okay. On a graph, do I have? Yeah, the length of a path is the number of edges in it. Did you do a proper what are paths? Nobody? Well, let's just do that little bit of review again. A path on a graph is going to be a way to get from point A to point B. Oh, and just a quick note. Disconnected graphs are heresy, and from this point forward, we will not consider them real graphs. Clear? Any questions on this? All graphs are connected. If they're disconnected, they are different graphs. Thank you for coming to my TED Talk. Okay, from point A to point B, a path is a way to get there. The length of a path is the minimum number of edges in it. Well, scratch that. The length of a path is the number of edges in it. So in this case, 1, 2, 3. If I add a little shortcut in there, let's say like this one, now I can make a path which is 1, 2. Okay, I really don't want my distances to be shortcut by shortcuts. So I probably want the distance to take the shortcut instead of the long path, the long way around. So we're going to define our distance as the shortest path to get from point A to point B. And our goal is to prove that this is indeed a metric on a graph. So to prove that it is a metric, we have, what was it, 4 things we needed to show? Starting at the top with the simple one. If I have a point right here, how can I go from this point to this point? Well, one way would be to go over here, and then down here, and then up here, and then back here, and then back to here. But that's not a very intelligent way to go from a point to itself, is it? Somebody help me out here. Don't move. Yes. Let's just not go anywhere. What's the distance from this point to itself then? Yeah, because how many edges are in the don't go anywhere path? None. Okay, distance from a point to itself is 0. We have that. QED. Next, we have to show that the distance from a point to a point that's different had better be bigger than 0. Okay, here's a point. Let's instead of go loops. Loops are fine. Just basic idea. Why are loops fine as far as we're concerned? We go big picture. What's a loop? Loop is finite. We don't care.
Infinitely many loops?
Infinitely many loops. All of those are contained within that vertex. Still finite, still don't care. Same thing with multi-edges. As far as I'm concerned, you can have as many multi-edges as you want. It doesn't affect the scale properties because it, well, you know, as we're defining distance, if distance is shortest paths and I could pick this edge or this edge and they're functionally equivalent, I didn't change the distance. I didn't change the metric. I didn't change anything. So we allow loops, we allow multi-edges, they don't matter. They never come up. Okay, so distance from a point to a different point. If I have, instead of picking a different point and showing that the distance has to be bigger than 0, because I'd have to do that for every point, let's instead just look at how many points can I get to from this one without doing anything. Yeah, I can only, if I don't go anywhere, I have to stay home. Okay, this is the only point distance 0 from itself. We'll call that good. Okay, next step on the hit parade is we gotta show that the distance going one way is the same as the distance going the other way. So let's say we have, let's just be real formal for a second, just to prove that we can do it if we wanted to. Let's say we have a graph G, B, a graph. And let X and Y be vertices of G, where distance from X to Y is equal to, what's your favorite capital letter?
N.
N. Our goal, prove that the distance from Y to X is capital N. Suggestions on how to start if suddenly I go from, what do we call it, a complete cavalier blunderbuss attitude of we don't really care about rigor to suddenly we care a lot? Why did I do that? It's like 10:30. Okay, so how should I start with this? We know that the distance from X to Y is N. That means that the length of the shortest path from X to Y is N, right? So let's grab that path. There is a path. And let's even figure out exactly what it is. It starts at X. It goes to, let's say, X1. It goes to X2. It goes to X3, all the way up. How many times does it hop? N many times. So it goes up to Xn. And going from here to here is my first edge, my second edge, my third edge. This is my nth edge. So I just made my nth hop. I'd better be at Y. So Xn is Y. Okay, what can I do with this path? Turn it around, walk backwards. Now I can go from Y to X with a path of length N, but we don't just want to show that there is a path of length N. We have one more thing we need to do, right? No shorter path, because the distance is the shortest path. Any suggestions on how to do that? Contradiction, everybody's favorite method of proof. Unless it's not, in which case you are objectively wrong. Okay, so let's assume to a contradiction that there were a path that only had, starting at Y, and went off, let's call it Y1, Y2, Y3, Ym, and let's say that is X. And we're going to assume to a contradiction that M is strictly less than N. Now what can I do with this path? Go backwards, and now I'm going from X to Y in only M hops instead of in N hops, and this is a problem because the distance from X to Y, there can be no shorter path than N. So contradiction achieved, QED. Okay. I'm really not counting my QEDs. I don't know if I should be, but
5 up. I'm pretty sure it's like 2. All right.
I mean, this is coming from, it's not her QED. I accomplished my goal, and I, in the first slide, we got 5 basically, so.
Yeah.
Okay, well, I actually fully support this. We should review the tapes. Okay. We had to prove that this was a metric. We got 0.1, we got 0.2, we got 0.3, right? Yes. One more thing we have to show. We have X, we have Y, we have some path between them. I have to prove that any path I don't have to prove anything here, do I? Distance can't be shortcut by a detour, If the detour were shorter, that's a shorter path, and so that's the distance, not a shortcut. QED. Is everybody okay with this? Do you want to see some formal things on the board?
I think we're okay with it.
Okay. 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 Take us up to the next slide. Ah, yes. We already remember isometries. Why do you think I'm going into it again?
Go ahead.
Because that was informal isometries. Now we're doing formal isometries. Great. Okay. We want an isometry is a map that preserves the distance, and now we actually know what that means between points. So, problem. Let's create a map that preserves distances between integers under the absolute value metric and a graph. Integers under the absolute value metric, everybody's clear on what that means? We're taking two integers, distance between them is the absolute value of them. This is how you get the triangle inequality as it was written. I'm not going to prove that this is a metric space unless somebody asks me to. Going once, going twice, sold to the guy who has no questions. Okay, so we have integers under the absolute value metric. Here they are. And they keep going. I need to make a graph and then build an isometry to it. Notice I gave myself a lot of freedom here. I don't say what graph I need to take this to. So does somebody have a favorite graph?
K3.
K through 3 is finite. I don't like it. The infinite path. I like the infinite path. It's pretty easy here. Why? There's the infinite path. And there's the integers. And what do you think my isometry is going to be? Where should 2 go?
0.
2 could go to 0. Okay, if 2 is going to 0, then where do you think we should send negative 2? Remember, if 2 is going to 0, negative 2 has to go somewhere that has, what's the absolute value of 2 minus negative 2? Or what's the distance from 2 to negative 2? 4. So negative 2 had better go somewhere that's 4 distance away from 2. You're saying we just shift everything over? Yeah, that's probably totally okay. If 2 goes to 0, we're doing 1 hop, 2 hops over. So then 2 would go 1 hop is negative 3, 2 hops is negative 4. Distance from 0 to negative 4 is still 4. It's a little bit more complicated than I had in mind for the first example. I was thinking just, how about we send a point right there, not move it? But it also works to shift everything over by 2. Quick proof, it's an isometry. I'm not going to do this because it's what you would do in first grade on the number line. Everybody remembers that? Think back. I know it was a long time ago. Everybody's good with this?
Positive 1 to negative 1 with the
Sure, that's another way we could totally do this. Let's build our little path graph. A second isometry, just for bonus QEDs, is to send, we want negative 1 to jump forward. We're going to send it right here. And we're going to send negative 2 over here, and negative 3 over here, and negative 4 over here. And then this is going to be 0, 1, 2, 3. That's still the same. Distances haven't changed. I just took my entire infinite number line up and flipped it around on its head. Awesome. We did this one twice. Jump me up to the next problem. Ooh, something a little bit more interesting. Create an isometry from an infinite path into the real numbers. So last time we went from integers into a graph. Now we're going from a graph into the real numbers. I'm going to just quickly draw the real numbers. All of them. The folks online are only going to see some of them because the camera isn't that big, but trust me, I'm drawing all of them.
Almost like they couldn't see Anna's proof.
Okay, there is all of the real numbers. Infinity's over here. Negative infinity's over here. I am taking an infinite path graph, and I have to drop it down onto the real numbers. So infinite path, it doesn't start anywhere. It doesn't finish anywhere. It just goes forever. But here it is. What do you think is a fair isometry on this graph? Yeah. Let's pick a point right here. They're all the same. It's infinite, goes on forever in any direction. Let's call this 0. If that's 0, well, next should be 1 or -1, right? Because there's only 2 points that are distance 1 away from this. One of them has to go to 1. The other has to go to -1. So 0 is going to go to 0. Let's call this one 1. And let's send it to -1. Okay, now 0 went to 0, 1 went to -1. How about 3? Where does 3 have to go? It has to go something that is 1, 2, 3 away from 0, and 1, 2 away from where 1 went, which is -1. There is only one point that does that. That's -3. Okay, nifty. We can, in this way, we sent 2 points. That tells us where every other point has to go. We've got an isometry between your infinite path and your real numbers. Everybody's comfortable with this? Okay, jump me up. Yes. This example is meaningfully different from the previous one. Why? Because in the last one, integers to infinite path, we didn't just build a function that took integers onto a path. I mean, we did. But that function also cleanly went backwards. It took the integers to a path. It was a bijection. We could totally just invert it if we wanted to. This function, not so much. I mean, I can tell you where 0 goes on the real numbers. But if I asked you to give me an isometry from the real numbers to this path, where are you going to put 1/2? Yeah, it's not going to happen. I don't know if I asked myself to prove that or not. You want to take me to the next slide and see how much work I've made for myself? Ooh, okay, this isn't so bad. Why is it impossible to create an isometry from a triangle into the real numbers? Now, first level analysis, you might go, well, a triangle has 3 points, real numbers are an infinite line, but that's not a problem. This has points, this has way more points, doesn't matter. Instead, we have a triangle. Does anybody have an intuitive reason why I can't isometrically drop this triangle into a line?
Distance 1 away from each other.
Yeah, they're all distance 1 away from each other. So just turning that into a proof real quick, if we did have a, proof by contradiction, the best kind of proof, yes, I will live and die by this assertion. If we did have an isometry from this triangle into the real numbers, this has to go somewhere. Let's say it goes to the point A. Okay, now let's label our vertices A, B, C. Where does B have to go? Well, it has to be distance 1 from A. So it can either go to A plus 1 or A minus 1. It's really symmetric, so let's just say we send it to A plus 1. Okay. Now where do I put C? I got nothing that's distance 1 from this and distance 1 from that. I can't do it. Explained. QED. Okay, take me to the next slide if you would.
Next slide, you want one more?
No, this is exactly what I want. Down at the bottom, we have A very meaningful definition that I'm not going to dig into nearly as deeply as it deserves. The Euclidean dimension of a space, the Euclidean dimension of a structure, is the smallest Euclidean space we can embed it isometrically into. So what's an embedding? I think that's defined on the next slide. We'll get to it when we talk about it. I can't isometrically map this triangle into a line. I can totally isometrically map it into a plane. We probably do that later, but it's not hard to see. That tells you that this thing, it can go into a plane, it can't go into a line, it's of dimension 2. Nifty. That's a geometric idea that lends itself nicely to being coarsened. Okay, take us to the next slide. Euclidean dimension, we talked about it there. Now we're doing a fun little example. Euclidean dimension of an infinite, that's not even an infinite path, that's a finite path. Okay. We already did this. I can map the path into the real numbers. Can I map it to a single point? No. So what's the dimension of the path? 1. Okay, nifty. Jump us again. Euclidean dimension of a triangle. We just talked through this one. Do you guys want to hear it again? Okay, take us to the next one. Ooh, that's a little bit more interesting. That's actually really interesting. Somebody want to go out on a limb and just take a wild guess? What's the Euclidean dimension of a square?
Probably 2.
You might think so. But think about it carefully for a minute. If I take this square I have here, and I were to just map it onto the plane in the most intuitive way you can think, well, I would take one corner of it to here, one corner of it to here, one corner of it to here, one corner of it to here. Distance from here to here, that's 1 as required. Distance from here to here, that's 1 as required. Distance from here to here is 1. Distance from here to here is 1. What's the problem? Yeah, what's the distance from here to here? Square root of 2. Thank you, Pythagoras. Lift a corner up. What's the problem with lifting a corner up?
We make it longer.
You'd be shortening some other paths.
Yeah, if I started dragging these corners in to try and fix that distance, I'd be making this one bigger. Or I'd be making these ones smaller. Lift a corner up in the other sense of lifting a corner up. What's the problem with that? We leave the plane. Okay, so the square doesn't have dimension 2, which is kind of weird, but this isn't a square in the square sense of the word. This is a square graph, a 4 cycle. Suddenly it seems less strange. You have a question?
So wouldn't the distance between those 2 points be 2 instead?
You're right. We need to somehow make it so the distance between them is 2 instead of 1. Still going to be difficult. We can't quite do that. And it's really...
I'm sorry, I'm just wondering, can we not have a distance root 2 between 2 points?
You missed the earlier, what should I call it? Dog and pony show? You missed the earlier dog and pony show about distances on a... We're going from a square graph into a plane. Distance from these 2 points, we're measuring it in the graph by the shortest path. We want to do this without changing the distance. So this distance had better stay 1 while somehow turning this distance into 2. Yeah, okay. So we can't put the square into the real number line. And in fact, I think I was going to say we could just lift a corner up and fold it to make that distance shorter, but that's not what we need to do, right? We need to make it longer. Suddenly, I don't think we can do that. You got a question for me?
Your argument only works for a square, right? So if it's a rectangle with side length,
Well, this isn't a square. This is a 4 cycle. It's a graph with 4 vertices, 4 edges. So this distance has to be 1. I can't change it around, make it something different. Okay. So what's the Euclidean dimension of a square? We'll get back to that because this one's even worse. How about that thing? That thing is a point. Then we've got 3 little spokes that come off of it. Okay. I can't map that into 1 dimension. I mean, if I did this, I could map these 3 into 1 dimension. This thing would just be hanging off the side. Can I map it into 2 dimensions? Well, no matter how I do it, this point right here has to go somewhere. So let's say it goes right here. Now, every other point is distance 1 away from it. That means that they all have to find a way to coexist on that circle distance 1 from it. Well, I can put this one right here. That's distance 1. And if I did that, there's only one point. It has to be, this one here has to live somewhere that's distance 2 from that. That's diametrically exactly opposite. That's distance 2. But now I need another point that's distance 2 from both of those. That's not going to happen, Chief. It's just not going to happen. Is it clear that this problem doesn't go away if I give myself 3 dimensions? This problem doesn't go away if I give myself 4 dimensions? No matter how many dimensions you give me, this circle only has 2 points diametrically opposite from each other. So I can never get 3 points all distance 2 away from each other on it. So this is where the idea of Euclidean dimension implodes upon itself and just it crashes and burns. I don't care how many dimensions you give me, this thing can't exist in the real world. Okay. That's okay. Why? This thing's finite. We don't care. Why did we do all this? Just because I really wanted to stress the geometry of what we're doing. Jump me forward. I think what we're talking about now, yes. Now we actually get to coarsening things. An isometry is a notion that an isometry is a map between spaces, keeps distances the same. My problem that I gave myself is to add math words to this definition. Think back to just briefly earlier in this talk. What are math words? It starts with an S. Symbols. We're supposed to translate the words going on into symbols. So, help me out here a minute. If I say an isometry is a map, in symbols, how do I say I have a map between 2 metric spaces? Well, I probably have to start with symmetric spaces, right? X and Y. And these have to be metric spaces, so let's give them distances too. Let X with the metric be X, and Y with the metric dy be metric spaces. Okay, great. We now have 2 metric spaces. I want to map between them. Remember, we do maps with this f from x to y. And we want to say that it's an isometry if it keeps the distances the same. So is an isometry if distance is the same. So I need to pick for all possible pairs of points. Let's call them A and B in X. We have that the distance in X, so distance in X from A to B, has to be kept the same. So it's got to be the same as the distance in Y between wherever I send A and wherever I send B. There. Okay, we did it. We translated this into math. Give me the next slide. Oh, look at that. I did exactly the same thing, but I did it with some different letters because I'm clever. Okay, give me the next slide. Yes. Quasi-isometry, coarse isometry, coarse geometry. The whole idea is that we're a little too restricted in the world we're dealing with, and I need to give myself a little bit of room to breathe. So we want to take this definition and we want to keep it as meaningful as possible while also blowing it wide open and giving ourselves some room to breathe. If you look at this definition, this is a philosophical question more than a mathematical one maybe. What's the strongest statement in here? What's the most powerful symbol I'm using? I think you've got it. I think, Ambrose, you may remember my rants about this from our college algebra class. What is the most important symbol in algebra? The equal sign. You got this, Hannah. Equals an incredibly powerful thing in mathematics. It means I can just pick up whatever's going on over here, and anywhere I see this thing, I can just drop this thing instead. And I don't have to worry about it because they are the same thing. So let's get rid of it. And let's replace it with a suitable facsimile of equality. Anybody have something that's a suitable facsimile of equality? Yeah, that's right. We make it wiggly. Hit me the next slide. Look at that. We made it a little bit wiggly. Oh, yeah. Okay. We don't want quite that. Well, that's exactly what we want, but we need to understand what that means. So this is the beauty of translating it back into math words, symbols. We want to turn that into something a little bit more rigorous. Jump me to the next slide. I think we do that there. Yes. We had isometry. Now we come to the two big ideas that I actually care about. One is a coarse isometry. One is a quasi-isometry. And the notion is that in a coarse isometry, this approximately equal to means something. What does it mean? I don't care. It just has to mean something. In a quasi-isometry, it has a much more restrictive meaning. It means roughly linear. What does that mean in much more, well, I guess we'll just follow the slides as I've written them. Why? Because I trust the decisions that Michael made at 3 o'clock much more than the decisions Michael is going to make at, what is it, 11:15 about how this talk should progress? Okay. So give an example of a coarse isometry that is not a quasi-isometry, i.e. we want to create a function that in some sense respects the distance, but certainly doesn't respect it up to being linear. Let's do this in kind of the most natural way I can think of. Let's make a function from the integers 1, 2, 3, 4, 5, and let's go down to the integers, but let's do it in kind of a clever way. Let's send 1 to 1, 2 to 4, yeah, you guys, 3 to 9, 4 to 16, 5 to 25, and generally let's just send n to n squared. Why did I pick to send it to its square? Yeah, that's not linear. It's definitely a function, but it's not linear. So our goal is to show that this is a coarse isometry, but not a quasi-isometry. What that means is it's got to respect distances, but not respect them linearly. Jump me to the next slide. I think I actually put that in words. I don't. Okay, never mind. I do put that in words pretty soon. And maybe we should, I do think we should go forward to that. Take me past this one. We may come back to it if, frankly, I think it's better if we, is everybody comfortable with where we're at? Okay, take me forward a little bit more. Did I not have this as a, okay, jump back.
go ahead, Michael. I think.
Okay, we're back. Where were we? We were trying to take a length space and show that it is quasi-isometric to a point if and only if it is bounded. Before I launch into this, let's just take a moment to appreciate what that says. Something is quasi-isometric, which is from this point forward. From this point forward, that's what we're going to mean by exactly the same. Two things are our new relaxed version of equality, a point and a bounded space. That's basically the line I started this whole talk with. If it's finite, it's the same as nothing. Does that check out? Everybody sees the connection here? Okay, so we want to take a bounded space and we want to show it's quasi-isometric to a point. Being quasi-isometric means that I can embed one and one. We don't know much about it except that distances are given by shortest paths, and here's a point. We know just about everything there is to know about it. It's got mass, it's got spin, and it's got a, what do we call it? Event horizon? It's a black hole joke. Okay, so we have a space, we have a point, we know this is bounded. I want to quasi-isometrically map this into this, i.e. I want linear distortion. Let's say this thing is bounded by some large, possibly large distance d. What's the most intuitive map to take this mess into this point? There's really only one way to do it, right? Everything has to go somewhere, and there's only one somewhere it can go. So let's just send everything to there. That's my quasi-isometry. Everything goes to the point. Going backwards, getting an isometric embedding the other direction, the point can go to that point. Doesn't matter, that point's just, a point. Okay. Going backwards, distance from this point at its image, it's a point. I don't have anything to do to show that's an isometry because there's no distances that can possibly change going from a single point backwards. Going forwards is a little bit of work, right? Because I can take 2 points and let's just play worst case scenario. I could have a point here, x, and a point up here, y. And what's the distance between them? It's going to be d. So if the distance from x to y was d, what's the distance between their images? Well, this is their image. It's the image of both of them. It's a point, the distance from a point to itself, 0. Distance between their images is 0. So can I put a bound distance from f of x to f of y? Can I put bounds on that above and below? Yeah, it's going to be less than or equal to 0 times the distance from x to y. And it's also going to be greater than or equal to 0 times the distance from x to y. And just for the fun of it, I'm going to add a plus 0 and a plus 0. Why did I add the plus zeros? It's not because I'm an analyst. Okay, exactly. It's because it's linear. Here I have a multiplicative factor, a slope. Here I've got my additive factor, an intercept. That's a line. It's a really boring line, but it's a line. So we have put linear bounds on the distortion of the metric. This point and this point are quasi-isometric. And that brings me to my favorite joke. Okay? Because now you might be asking me, this is really cool and all, but what's the point? Well, that's a point. That's a point. And this thing over here, This is a really, really big point. And this is just a mess. And all of them are quasi-isometric because they are bounded. And that is the point. Okay, take me to the next slide. Oh yes, I put this one here just to remind myself. You are here, we're about halfway through. Yeah, we're pretty close because we started at 10 o'clock, right? Yeah, we're doing good. Okay, now we can get to the joke, but in slide form. Take me to the next one. Take me to the next one. Look, a point. Take me to the next one. Look, a big point. Take me to the next one. Look, a mess. And all of them are quasi-isometric to a point. Great, and that's the point. Okay, you have a question?
Yeah, is there any real world applications for this?
I'm sorry, do you want to come up here and ask that question again? Can you say that again for me?
Is there any real world application for this?
What an interesting question you've got. And I'll think about it while security, would you take this guy to the door, please? That's you. Okay. With that out of the way, yeah, there's real world applications. Thank you for asking. I'm glad that we all care. This is a math talk. If you care about that, let's just not. Take me to the next one, okay? That line right there, that is not quasi-isometric to a point. Why? Because it's not bounded. Why is not bounded not quasi-isometric to a point? Well, suddenly, this distance, if this blows off to infinity either direction, I have a very small problem. This function's not going to tend to infinity. I probably should have put something about that here. This is probably actually going to be just 1, and then this is going to be less than the distance. You know, it's just less than the distance. I don't need to put anything on that because this is bigger than 0, this is 0. It's definitely less than. This thing here, we probably still want to be a 1, but this thing over here, we'll just put a minus d for the diameter of this set. Okay, that was a little, what do we call them, a blooper? These functions are supposed to tend to infinity as the distance tends to infinity. Now they do. It's just this distance can never get bigger than d, so my little additive factor corrects for that. If this space were unbounded, there is no additive factor I could use to correct for that, and I wouldn't be able to drop these two functions in there, and it wouldn't be quasi-isometric to a point. Awesome. Okay. Take us forward one more slide, because that line is quasi-isometric to that mess. And that's the point. Okay. Now I have made the joke. That was my favorite joke. Thank you for coming. Take me for, here we go, yes. Okay, now we get to some interesting, I wouldn't dare say serious because it's basically midnight. I'm not going to be serious. But
Rounding
all right, you get me talking and it'll be Sunday before I realize it, so. Okay. This talk isn't called coarse geometry. This talk is called coarse graph theory. There's a big, important reason for that. There's 2 of them. And they are what man, I was a joker when I made these slides. They are what I lovingly refer to as the 2 finest results in coarse graph theory. Those are that every length space is embeddable, quasi-isometric, or is embeddable into a graph. And any embedding into a graph, even if it's just a coarse embedding, is actually going to just also be a quasi-isometric embedding. And I think that we should prove both of those results. But first, let's just recognize the little fact that take those on faith for just a minute. Every length space, everything with a meaningful idea of paths, I can put into a graph coarsely. But then everything I can put into a graph coarsely, I can put that into a graph quasi-isometrically. So really, every question I could possibly ask you about meaningful notions of paths, I can turn into a question about quasi-symmetries on graphs. And that's pretty cool. So I think we should prove that. There he is. Problem. Let's take a length space, and I guess I'm proving the top one first. How creative of me. Let's take a length space, and let's take a graph, and let's assume that we have a coarse embedding from that length space into the graph. So we have a length space, which is x with the metric d, and we have a graph g. And we know that there is a coarse embedding between them. What does that tell us? That tells us that there is some rho minus, such that if I take the distance, and I think this is the distance of x and y, where x and y live inside of the length space x, I can get a lower bound on the distance between them in the graph. And an upper bound. I can hear Nana seething in the back about how that was phi, not rho. Okay. We have these functions, they exist. We have here distance in the graph. Distance in the graph. Did you have a... I can go to basically whenever. What do you guys think? Okay. So these two results are the only things I truly care to prove. Like, this is the entire point of the talk. So, all right. I will plan till, Alec, how much material do you think you got?
I have 2.5 approximately. A lot of gimmicks that can be short.
What we're trying to prove. This is where I want to start. Why? Well, because I don't know really much of anything about this rho minus function and this rho plus function. I just know that they exist. But this thing right here, that's a distance on a graph. That's a path. So this tells me that I have a point here, x, and a point, I guess this is f of x, right? And then I have something way over here. This is f of y. And I've got a path between them. And this path, it's a path in a graph. It's made up of edges with vertices. So I don't want to look at so much the distance between x and y. I want to look at this path chunked out into these little bite-sized nuggets. And each of these points, I don't know so much. I know the distance between them is 1. So I can put, instead of dealing with y over here, I've got this x1 is the notation we used to call it. So call this f of x1. All right. So I have, we want to do this in a slightly, different way, but this is where we're at. So I'm gonna do it this way, and it'll work fine. Okay, so the sketch big idea is this path broken into bite-sized pieces. Each of those has distance 1. That means I'm no longer dealing with this arbitrary rho minus function of some distance I don't know anything about, and this rho plus function of some distance I don't know anything about. Because if I substitute in here instead of x and y, I pick just the first point on this path, well, suddenly the distance is 1, because the distance is 1. So I have, this is what I mean by I wanted to do this slightly differently. We should be going from a graph to a length space instead of the other way around, because I want my distance I'm starting with to be a path I can break apart into bite-sized chunks. So that's what I'm going to do, because I'm not going to figure out how to do it the other way right now. Okay, so we have a distance on the graph, its length 1. This point has some image, this point has some image, and they're bounded by rho minus of 1 and rho plus of 1. And then this point x1 has some image, this point x2 has some image. And their distances are going to also be bounded by rho minus of 1 and rho plus of 1. And I take one hop, I move at most rho plus of 1, I move at least rho minus of 1. This total distance is dxy. Well, I know that that means I take dxy hops, and at each hop, I can move at most rho plus of 1, and I have to move at least rho minus of 1. What does that tell me that my distances are going to be bound by? dxy times rho minus of 1. If I hop the minimum amount every single time, or if I were to hop the maximum amount every single time, I would just change this from a minus to a plus. And I guess just to be a little bit better about it, that means that the distance in the so we're going from a graph onto a length space here instead of the other way around. That means the distance on the graph is going to be at least the minimum number of hops, the minimum length a hop goes to, times the number of hops. And then this is the distance in the length space, or in the image, let's just say. And that's going to be bound by this rho plus times the number of hops. Okay. Now, why is this special? I still have these rho functions. But that's the rho function of a constant. And a function acting on a constant, it's constant. I don't care what it is. I don't care what constant it is. That's a constant times my variable. That's a constant times my variable. These are both linear functions. That's a quasi-isometry. Everybody okay with this? Okay. So what does this tell us? This tells us that if I have a coarse embedding from a graph onto a length space, that's actually a quasi-isometric embedding. Great. The next one I want to talk about is creating embeddings from an arbitrary length space into a graph. So this time we actually do want to start with a length space. Big picture for a second. What that function tells us is that if we're in the world of graphs, there's really no distinction between a coarse embedding and a quasi-isometric embedding. Okay, now we want to show that anything in the world of length spaces we can think about in the world of graphs. So here we have a length space. And length space, remember, just means that there's some meaningful notion of a path between things, and that's closely related to their distance. I want to create a graph that looks like this length space. Any suggestions on how to start? Make it squiggly. I do like the idea, but it's not quite what we're having in mind. So a graph is a bunch of vertices and edges, right? Let's start with vertices. Let's just start dropping vertices in here. Okay, we dropped a bunch of vertices in there. Now we probably need some edges, right? Okay, let's be a little bit more careful about how we create our edges. This vertex, what other vertices do you think it might be reasonable for it to have edges to? How about this one, this one, this one? Okay. Let's be a little bit more systematic about both these processes. In the end, we're going to want to take this space and we're going to want to kind of pinch down the whole bubble around this vertex to map down into that vertex. If when I'm doing that, I want to bound the distortion of the distance, I better bound that pinching notion. So I better have a vertex close to every point. So let's fix epsilon. That's 3, not epsilon. We could also use 3. 3 is a perfectly valid choice for epsilon. So let's fix some epsilon, and let's drop these points all throughout our length space so that nothing in the space is further than epsilon from a point that I've dropped down into it. Is it clear to everyone that I can do this? Yeah, if there's some point not within epsilon, now it's within epsilon. Okay. Now I want to add edges between points. Sort of the first level analysis might be, well, let's just add an edge between 2 points based on this epsilon, right? Yeah, close enough. If I just connected 2 points, if they were within epsilon of each other, would that work? Not quite, because I could have a point here and a point way over here, and there can be a whole whopping 2 epsilons of distance between them, and they can still cover all of my space. I mean, there's a whole whopping 2 epsilon there. I better connect with a little bit more distance than just epsilon. In fact, I think maybe 2 epsilon sounds appropriate. Or even better, let's connect it to 2 points if their distance is less than or equal to twice epsilon. Let's connect them with an edge. Okay, that creates a graph. And it also creates a very, maybe this one goes like that goes like that. Maybe there's no edge going on here. There's probably one here. You guys get the idea of what's going on. I better drop a point there. I'm going to be too far from things. There's a graph, and it looks like a fairly decent approximation of my length space. Let's prove that it's a quasi-isometric approximation of my length space. We're going to prove this by, well, I said there's a very natural function between this length space and this graph, right? The idea is everything in this length space should go to the point that it's closest to. Okay. Let's take 2 points in the length space. Let's say this one right here and this one right here. And let's think about what could have happened to the distances to the distance between them in the graph. Well, I guess I shouldn't pick points in the space that are vertices I've dropped, huh? Maybe instead let's take this point right over here. I should do this in a different color. Let's take this point right over here and this point right up here. And now our goal is to show that there's a linear bound on the distortion of the distance between these points. How I'm going to do that is I'm going to look at the distance between their images, and I'm going to use that to build a path in the length space that's pretty close to the distance in the graph. That sounds like a strategy? Let's do that. So here is my point. Here's its image. Goes to right there. Here is my point. Here is its image. Those 2 points are points in the graph, and so there is some path in the graph between them. Goes from here to 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 here, and maybe up to here, here, and here. And let's just pick that path. It definitely exists. And now let's follow it, but in the length space. I'm going to, from here to here is a distance of 1. And so that means there's an edge between these 2 points. That means their distance in the length space was, at most, 2 epsilon. So going from here to here, I cover, at most, 2 epsilons of distance. And this point maps down onto that point. And that be systematic. That happens for every edge. Every edge I hop translates to a hop in the length space of at most 2 epsilons. Okay, that gets me from one endpoint of the path to the other endpoint of the path with hops of at most 2 epsilon and the number of edges in the path, number of hops. I've moved at most twice epsilon times their distance in the graph. A minimum on this, well, this is a length space, so shortest paths are also my metric in the length space. If the shortest path in the graph were if the shortest path in the graph is, if there's a path substantially shorter than that in the length space, then we can grab points along that path in the length space and then grab their images in the, when I say along that path in the length space, I mean take points in that length space that are at most epsilon from each other. I have a path, I can subdivide it into a whole bunch of epsilon chunks. Let's do that. The images of each of those points are going to be points in the graph. That's going to give me a path in the graph. But a path in the graph going backwards, what we just argued here, is it can only grow by so much. So if I take a short path in the length space, I put it in the graph, it better pull back to a short path in the length space. Okay, nifty. We haven't accounted for this little chunk of distance at the ends of the path because I have to go from this down to a point there, but that's also not a problem. Why is that not a problem? Yeah, in fact, it's at most an epsilon, right? And over here, it's at most an epsilon. So we're thinking kind of we'll do 2 things. Quasi-isometry, I'm going to define it in a very, very lackluster way. Ready? Small distances can't get too big, and big distances can't get too small. That's all it really is. So small distances, they can't get too big because they do map to paths in the graph, and pulling those backwards, they only blow up so much. Small distances can't get too big. Big distances, they can't get too small. I should be way more careful about this than I am, but I'm not going to worry about it. Why? Because I'm not. Okay, going from here to here, I've moved an epsilon. Going from here to here, I've moved an epsilon. These two things together is a 2 epsilon. Now, each of these hops is a 2 epsilon. So the total motion I've got going on here is epsilon plus 2 epsilon times the number of edges. That's linear. 2 epsilon is my additive. Epsilon times the number of edges, that's my slope. Everybody's okay with this? All right. This really does deserve a lot better of an argument than that, but I'm not going to worry about it. Okay, I'm good with this. Take me forward. Oh, no, I just did, yeah, I did. I think I've done both of those. One is we did the first one, which is inside. Let me recap because they really are interesting and they are nice results. They're not complicated, they're actually really simple things, but let me recap. Inside of a graph, there's no difference between a coarse isometry and a quasi-isometry. These are the same notion because edges make your paths into discrete little chunks, and bounding the discrete hops bounds the entire path by some scaling factor of that. Then, by dropping these little points all over my length space and just contracting the balls around them and hooking up a bunch of edges, I can turn any length space into a graph. So I can turn any problem about anything coarse into a problem about graphs, and any problem about graphs into a problem about quasi-symmetries on graphs. Okay, great, now we can go. Let's not do that. We're going to jump into some of the more interesting questions. Why? Because we can. Okay, let's start with this. Goal is to make 2 graphs that are both unbounded but not quasi-isometric to each other. Any suggestions on how to do that? Well, they both have to be unbounded, right? So let's make first one a very simple unbounded graph. Let's make it our infinite path. And then I want something that isn't going to be quasi-isometric to this in any way, shape, or form. So it's got to look very different from this. Let's say instead of having an infinite path, I'm just going to draw it like this without the vertices. Why? Because we're looking at it from way far away and the vertices just shrink down and we don't care. Okay, let's start adding a whole bunch of little spokes coming off of it. And let's make these infinite as well. And these are going, so there's 2 graphs. This path extends infinitely in both directions. This path extends infinitely. These little fingers extend infinitely. Why are these graphs not quasi-isometric? Well, let's imagine that I had a function between them that was a quasi-isometry. That means that a point here and a point here have to go, let's not do that. I think I want to go the other direction. This point here has the area around it. Yeah, this is the way. This goes off forever back this way. This point here has some image up in here. Let's say it's this point right here. Now, coming off of this point, my distances can grow in 3 different ways. I can start moving down this way and they start getting bigger and bigger and bigger. I can start moving over this way and they get bigger and bigger and bigger. And I can start moving down this way and they get bigger and bigger and bigger. Okay. So let's take one of these points, maybe this one. It has to go, take a really far distance over this way, grab a point. It has to go somewhere. Let's say it goes somewhere way over here. Let's grab another point somewhere over here. Let's say it goes somewhere way over that way. Now, I've already moved way off that direction, way off this direction. Take another point way down here somewhere. Why can't it go anywhere? I'm out of directions. I just am out. Can I make that a little bit more formal? Yeah, we could. But I'm not sure exactly how I want to do that. The image of this finger, that finger is unbounded, and so its image has to be unbounded. The only way I can make the image of a chunk, a piece, unbounded is to use up... I want to jump forward to some quantized stuff because that will make this much more approachable. So I'm going to jump a bunch forward. There's going to be some... Oh, there's my definitions. Finally.
So forward.
Yeah, let's keep going a little bit. I have a couple of problems that are... Keep going. Hold on for a second. Nope, keep going. Jump back, jump back. Okay, yes. It took me this long to talk about connected graphs. Let's talk about connected. Okay, in a graph, we have a nice definition for when a set is connected, right? A set is connected if any 2 points in the set, you can find a path between them. Our goal is to coarsen this notion of what it means to be connected. We want to talk about coarsely connected things. To coarse an idea generally means to translate a notion about equalities or strict limitations on distance to a much more nebulous notion of restrictions on the distance. So, a set is connected if inside of it there's a path. And a path, there is a path from any point in it to any other point in it. I.e., if x and y are inside of, let's just call it some set A, then there exists this path with the first vertex being x and the last vertex being y. And I can hop along it. I shouldn't be drawing more edges. It has vertices. Let's call them x1, x2, and x3, so forth. And these vertices have conditions. X is the first one, so let's just call this x0. And let's call this one xn. x0 has to be the point we start at, x. The last one, xn, has to be the point we end at, y. And we have this nice little, what's the distance between these 2 points? It's 1. So, and the distance between x, let's just say I and I minus 1 is equal to 1. Okay, great. Where am I going to attack? Where's the very strict notion of distance? Right there. We want to, instead of saying distance is 1, 1 is a finite number, is bounded. Let's just say that 1 can be big, but not too big. Let's say it can be at most some m. What is m? A big number. I don't really care what. we're going to call this new notion of what it means for a set to be connected, M-connected. The notion of M-connected we now define much more rigorously. We now are going to take that discussion we had and we're going to turn it into a definition. So take a set. We're going to say that set is M-connected if I can find a sequence of vertices. Maybe they're not connected by edges, but they're all in the set and going from one to the next, to the next, to the next, to the next. Each hop is no more than some distance, well, then the distance we fix in the beginning, m. Each hop is at most m. That's what we mean by an M-connected set. Okay, neat? Okay, is this, yeah. That's the definition there. Then it should on the next slide have it in exactly this M notation. Jump us forward again. There it is. Now jump us forward one more. Okay. Show that for, okay, this is a notation that in my earlier jump forward a bunch to get us to some quantities. We skipped over what is an AB quasi-isometry. So quasi-isometries are linear distortions on the bound of distance. AB quasi-isometries just mean that those lines have slope A and additive intercept B. Everybody's cool with this? Okay. So what we want to show is that if we have two spaces, and we can just think about graphs, we have two graphs, and we have an AB quasi-isometry between them. We want to start with a connected set, and I want to show that that goes to a set that is M-connected. So start with a connected set over here. It goes to a set, possibly a whole bunch of just disjoint vertices. Maybe there's a little clump going on down here. I want to show the set it goes to is M-connected. How are we doing? We're doing fine. Okay. So to show that this is M-connected, I have to find one of these paths with hops at most M. What's the most natural way to do that? Well, let's jump back to this set, which I know exists. This set I know is connected. This set is its image. So this is the image of some point x, and pick any other random point we want down here. This is the image of some point y. X and y, they're points, they have to exist in here. X, y. There is a path between them. A pretty good candidate for my path with bounded hops is going to be this path. In fact, this path has x0, x1, x2, x3. It's got these points right along it, and each of those points has an image. This is going to be f of x1. This is going to be f of x2. This is going to be f of x3. You get the idea. Now, this is an AB quasi-isometry, means that my distances, this distance was 1. It got distorted by a linear function, a and b. So now it's going to be 1 times a plus b. Well, not it is going to be, but it is at most this function. And what did I say that we're picking m to be in this problem? Bigger than a plus b. So this is less than m. This is less than m. This is less than m. Every hop along your path, still less than m. Okay, great. M-connected is meaningful in a certain way because we can take a connected set, and as long as we put bounds on the constants on our isometry, we're going to get an M-connected set. Jump us forward again. Okay. Yeah, let's do this. I had a couple more metric problems like this with constants, but one's good enough for us to observe the pattern. There's a nice pattern. Ready for this? There's four things to jump through here. Ready? We take some geometric idea, some graph theoretic idea, like a connected set. We translate it into a condition about distances. We take that condition about distances, we relax what we mean, we relax the restriction on that distance, and then we want to try and show that the idea we've created is meaningful in some way. Okay, we will do like maybe one or two more of these kind of problems. I'll leave you with some fun food for thought, and then I'll turn it over to Alec. For those of you who've walked into the room, we're running behind schedule. Okay, so let's start with, just jump me forward. I know, but his students are waiting, and I don't want to make them wait too long. Okay, so here's a nice thing to talk about. We have the neighborhood of a vertex. In graph theory, what is the neighborhood of a vertex? Well, it's every vertex that shares an edge with that vertex. If this is x, then this is what we call the neighborhood of x, the neighbors of x. But our goal is to turn that into a metric condition. Instead of having a neighborhood of a set x, I mean, that is perfectly meaningful, but it's not hard. Somebody shout to me, what is the metric condition for a vertex to be in the neighborhood of x?
It has to be connected by one.
Yeah, there's exactly one edge well, there is an edge connecting them. They are distance 1 from each other. So if the neighborhood of x is all of the vertices that are distance 1 from it. How are we going to coarsen that distance equals 1? We're going to do it in the same way we did it for connected things. Distance 1, we're going to translate to distance at most m. And I bet if you hit the next slide, that's probably what I have there. Okay, I guess I left this up as a problem for me to talk about, but we did. Coarsen the idea of a neighborhood of a vertex. Well, the ordinary idea, the mundane graph theory notion, is that it's all things that are distance 1 from it. We're changing that to mean it's going to be all things that are distance less than m. And now we've attached this scale m to our problem. So instead of talking about the neighborhood, we're going to talk about the m neighborhood. Okay, now our goal is to show that the m neighborhood of the image of a connected set is connected. We talked about the image of a connected set in the last problem. We have a connected set. Its image is everything that, comes from something in there. And we already proved that that set is m-connected. So now we're taking m neighborhoods, we're taking an m neighborhood around it, and we want to show that's connected. Connected just means that instead of being able to find a path between the vertices with hops at most m, I need that entire hop to be contained in the set. Well, the hop's at most m, and I just said that everything that was within m of my set is going to be in the m neighborhood of my set. Is there anything else I need to do? No. Suddenly my set, I'm just taking a big bubble around it and adding all of that into it. And now it's connected. That's why we like m neighborhoods. It lets us take, if you take a neighborhood around things, then you get back connected sets, which is cool. Take me to the next one. Okay, now we're going to switch approaches a little bit. I have, okay, we're going to switch approaches a little bit. Instead of taking something that is a graph property and translating into a metric one and kind of turning it around, playing with it, getting a natural idea for what its coarse equivalent should be. Another fun and interesting kind of problem is to consider properties a graph that can have that are invariant or unchangeable under bounded distortions of the distance, under quasi-isometries. So I bet if you hit the next slide, I'm going to have one. Yeah. Okay, never mind. What I have is a bunch of fun properties of graphs that you can do that are quasi-isometries. And these ones are totally manageable. I've lost track of how my slides are put together, so forgive me. I'm only reading the first word in every sentence, and I'm not saying what's on them. Okay, we're just going to handle the problems that come as they come until we get bored of that. So we have a graph, and we want to prove that if I were to take every edge in this graph, and I were to drop a vertex in the middle of each edge, subdivide it. So I'm going to split this edge, drop a vertex right here, split this edge, drop a vertex right there, split this, you get the idea, split every edge, put vertices in them. I want to prove the new graph I have produced is quasi-isometric to the one I started with. Okay, to prove it, I have to show that there's a bound on how much distances can change. So let's start with two things that have, let's start with two vertices, x and y, that have distance x, y. Let's say that I should probably be doing my two graphs. We're just going to do it up here. This is the original graph before the splitting. Has a vertex here, a vertex here, vertex here, vertex here. And then, let's see, this just connects like that. Then I guess I have to split this edge. Nope, that edge is already split. I have to split this edge. Okay, there's my graph before the split. There's my graph after the split. Pick two vertices in here. Let's say this one and this one. The shortest path between them, it has some length, one edge, two edge, three edge. Great. Now, in this graph, what happened to that path? Yeah, every edge got split, subdivided. It's now two edges. So distances grow by, well, they exactly double. I could be much more rigorous about this and turn that into upper and lower linear bounds on the distance, but they double. They exactly double. Everybody's good with this? Okay. So that's a quasi-symmetry. Give me another fun problem. Adding many edges between pairs of vertices. Did I do the last one right? Did I read it right?
It says a different thing.
Oh my goodness, it says adding an edge, not subdividing an edge. I can't read these slides from here. That's
QED count is all messed up. We gotta keep a.
So I was gonna save this joke for the end. I was gonna save this joke for the end, but you know why the QED count is all messed up?
I mean, coarsely.
What does that number look like to you?
That's a 6, isn't it?
Finite.
It's a finite number. Okay, so now we're going to do a slightly different problem. We're arguing that we're doing fine. We are arguing that adding many edges between pairs of points with distance bounded by something produces a quasi-isometric graph. So here I have a graph, and I'm going to pick a pair of points on it, and we're going to make that a pair of points whose distance is at most m, and we're going to add an edge. So maybe these dashed edges are going to be the edges that exist in my new graph, but not in my original one. Then I'm going to pick some other points, maybe these two, and I'm going to add an edge. And then maybe these two, and I'm going to add an edge. Okay. We want to prove that this new graph I've created is quasi-isometric to the original one. And we're just going to prove this in my favorite way to think about it. Things that are close have to stay kind of close, and things that are far have to stay kind of far. So, take two things that are close in the original graph, like these two things. They're close. There is a short path in the original graph between them. I'm adding edges here. I'm not removing any edges. So the path that was there is still there. And my distance can't get any bigger than that. It can only go down from there. Okay, great. The other direction around. Let's take two things that are really far apart from each other. Clearly, I can shortcut that distance because I'm adding edges that might span large leaps. But let's take a path in my graph that's using my shortcut edges, like maybe this path. This edge right here, I can pull it out of that path, and I can substitute in instead taking the long way around, which is at most an m distance. So if I do that for every edge in, worst case scenario, every edge in the shortest path in my new graph is a brand new one I created. Well, every single one of them I can just substitute in a path of length m. So my path grew by how much? Well, the distance multiplied by m. Points that are far away, when I start adding these edges, do that whole argument in reverse, the distance shrinks by at most a factor of n. Worst case scenario, I'm dividing it by m. Great, points that are far away are still going to be far away because m is small in comparison to what I mean by far away. Good, good. Okay, jump me to the next one. Now we're talking about removing an edge. And I am going to, you could prove this in the same way, but I'm going to take a much more, my preferred way to prove this. Removing an edge produces a new graph. So if I take an edge and I remove it, I have a graph. And I want to prove that this graph is quasi-isometric to the one before I removed the edge. How am I going to do this? I'm going to add the edge back in. And the last theorem, problem, shows that adding an edge produces something that's quasi-isometric. I got something that's quasi-isometric by adding the edge, but that's where I started. So removing the edge, I go back to where I started again. Point is, if I can add an edge and I get something that's quasi-isometric, well, I can remove the edge and then add it back, and I have a quasi-isometry going between them. Is that clear? Or do you need a little bit more something to sink your teeth into? So let's say I have G, and I have G prime, and G prime is the graph G minus an edge. So the other way to think about that is that the graph G is G prime plus an edge. And the last problem tells us that this adding an edge means I can go quasi-isometrically back and forth here. So this problem, if I can think about instead of removing an edge, adding an edge, I can grab my quasi-isometries from here, and they still work here because this is the same G prime and this is the same G. Okay, great. Let's jump to the next one.
So maybe my question is sort of implicitly answered by this.
Go for it.
I don't think about infinite graphs that often.
Nope, that's okay.
It's important when you're adding edges that you're adding them between vertices whose distance is bounded. Is it just sort of not sensible to think about something like an infinite cycle?
The reason that I add them here between things with a bounded distance is because I need that cap on the distortion of I need a cap on that distortion. more directly, your question is it meaningful to think about things like infinite cycles? And the answer is yes and no. If I have any concrete structure you grab out of your graph, a cycle, what is a cycle? Well, a cycle, I mean, you can define it in a bunch of different ways, but the definition I use, a cycle is a path whose first endpoint is its last endpoint. And so that cycle is a definite path. It has a definite length. It's a definite object. It can't be infinite. Is it meaningful to think about an infinite cycle? Maybe, but I don't have an example of that off the top of my head. Does that help you?
Yeah, I mean, obviously, if it somehow is like, okay, here's a cycle that has an infinite number of vertices, I take out an edge, and these things that were at distance 1 are now at infinite distance. Obviously,
Yeah.
that we're saying I have a finite cycle that I can look at. It has m vertices on it. I take out an edge. These things were at distance 1 now they're at distance.
Okay, no. In that context, no, we don't. A cycle in your graph is a cycle, and it has some length around it. Okay, good. Okay, is this the new one or a new one? Okay, removing many edges. This is the same argument. I mean, if I can remove one edge and get a quasi-symmetry, then I can, there is one thing to be careful of here, which is that we can't do this by induction because we're dealing with infinite graphs and we could be removing infinitely many edges, and that's dangerous. But it's the same argument here because the first problem we proved wasn't add an edge, it was add a bunch of edges. And so the same argument holds with remove a bunch of edges and then add them back in, and you have quasi-isometries go in both directions. Good, good. Jump us forward again. Okay, this is, I don't know what I was reading earlier because this is the first one I started with. Subdividing every edge a bunch of times. So we have a graph. We're going to take and here's a graph. We want to subdivide every edge m times. What is m? Some natural number. And we want to prove that that produces a quasi-isometric graph. Well, I don't see any reason to be more fancy with this than I subdivide, take your shortest path, I subdivide every edge m many times, every edge turned into a path of length m plus 1. Now, that means that the distance grew by m plus 1. Take a shortest path in the subdivided edge, do your contractions. Every path is going to shrink by a factor of m. That means that your shortest distance in the original graph, you're only going to be different by a factor of m either way. That's linear. We don't need to worry about it. Sounds good? Good. Okay, jump me to the next one. Subdividing each edge in a set. Okay, this is the same thing, but we're just subdividing some edges instead of all the edges. Let's jump forward. Contracting a single edge produces a quasi-isometric graph. That's not too interesting. I'm going to talk through I'm going to look at this, I'm going to acknowledge that it's true, and then we're going to jump forward. It is important to acknowledge that it's true. Why? Because this is kind of the bread and butter of what you need to do a lot of fun and interesting things. But take an edge, contract it. Any path in the graph couldn't have grown because I contracted the edge, and it couldn't have shrunk by more than 1. That's linear. We're good. We don't need to worry about it. Jump us forward to the next. Contracting a set where the connected components are uniformly bounded produces a quasi-isometric graph. Okay, so first level analysis. We're taking, instead of just a single edge inside of this graph, we're going to take some set inside of the graph, something like this. and we're going to contract it, i.e. we're going to identify every vertex in this set to just be one vertex, and all of the edges connected to any of them are going to go to that new vertex instead. Everybody's clear on what it means to contract a set? Uniformly bounded. So this set is bounded means that there's some maximum distance points inside of it can be. Here, we're contracting a set where the connected pieces are uniformly bounded. That means that there is some bound that applies to all of the connected pieces of the set that I'm contracting. So, the set I'm contracting might not be connected. There could be some part of it here, some part of it here, some part of it here. But they're uniformly bounded, as in there is some bound, so that every single one of these pieces has diameter bounded by that thing. This is different from the connected components just being individually bounded, because this might have a bound M1, M2, M3, and then M4, and these M's might just keep getting bigger and bigger and bigger off to infinity. So no matter how big, I can find a set that's bigger than that is still connected. Uniformly bounded means that there is some M prime such that the M1, M2, M3, all of them are less than that M prime. Does that answer your question? Okay. So we want to say that contracting a set where the connected components are uniformly bounded produces a quasi-isometric graph. This one kind of has a cute little picture I like to draw. So here's a path in my graph. Here's an endpoint. Here's an endpoint. Now I'm going to contract uniformly bounded pieces in this. Well, those uniformly bounded pieces account for, at most, some chunk of this path. That contracts to a point. That might contract to a point. These have to be disconnected, otherwise they're the same connected component, right? So that contracts, that contracts, that contracts, that contracts. Each of these contracts to a point. They're shrinking from this point to this point. These sets are of bounded diameter. That contracts by at most m. Rinse and repeat that for each of these. Distance only shrinks by a factor of m. Everybody's good with that? Okay, jump us to the next one. Prove that contracting sets that are each bounded but not uniformly bounded might be a little bit of a problem. Easy example of that. So I'm going to contract, this is going to be my first set. This is going to be my second set. This is going to be my third set. And so forth. I'm taking an infinite path. My first set is the first vertex. My second is the next two. My third is the next three. My fourth is the next four. So back to your question, each of these sets is bounded. The nth set is of diameter n, but they are not uniformly bounded because for any m, just pick something bigger than that, and that set is going to be bigger than that bound. Does this check out to you? Okay. So we want to prove that this is not a quasi-isometry. What that means is that there is no linear bound on my distortion here. So let's assume that there were a linear bound on the distortion. And what that would mean is that if I take 2 points that are far away from each other, they can't get too close. How far away? Well, that depends upon the exact constants of your linear distortion. But it's a linear function with some positive slope. Eventually, there is a distance that can't shrink to 0 as soon as you pass through your additive constant of your linear function. Is it clear what I mean by this, or do you guys want to see some numbers? Okay. So let's say that we're only going to worry about the lower bound. We're going to say that we're assuming to a contradiction that we have a quasi-isometry, and so we have lower and upper bounds on the distortion of distance. That means there is some a such that the distance from x to y times a, and then this is a lower bound, so we're going to be subtracting b, and just to keep our life easy, we'll make a big number, and we're going to be multiplying by 1 over a. So this is a linear function that's shrinking that distance. This is how it can't shrink more than this. So this has to be less than or equal to the distance between their images. That. Okay. If it's a quasi-isometry, then there is such an A and there is such a B, such that this thing has to happen. But because these sets are not uniformly bounded, I can make this as big as I want. How big do I want it? Well, I probably want it big enough such that 1 over a times bx y minus b is greater than 1. Just doing a little bit of scratch work here. We're going to multiply both sides by a. So we get an a here. Then we're going to add a b to both sides. Hey, a plus b, that's kind of a familiar number we've seen before. Okay, so now proving that we break this, a plus b, a and b are constant definite numbers. A plus b is a constant definite number. These sets are not uniformly bounded, so I can find one with diameter more than a plus b. Pick that set. The diameter is more than a plus b. That means there's a point x and a point y inside of it whose distance is more than a plus b. So this thing is a plus b. I'm going to divide that by a. I'm going to subtract b. I probably made a mistake in my scratch work there, huh? Because I probably want this to be a times b. Because I want, when I divide by a, and then let's just add an a to that. So we're taking a set, everywhere I said a plus b, we're going to use a times b plus a. Take a set, 2 points more than a times b plus a apart from each other. Divide that by a. Now it's b plus 1. Subtract b. This is 1. So the distance has to be greater than 1. That's not what I wanted, is it? No, yeah, distance has to be greater than 1, but I'm contracting the entire set to a single point. Single point is only distance 0 from itself, and so I broke it. There cannot be a quasi-isometry there. Is this clear? Okay. I love how one person nods, and I look at that and I go, everybody understands what's going on. Okay. Jump me to the next one. Another interesting question. Ooh, yes. I am now, how are we doing on our time? Yeah, we're close enough that I am done with proofs. Now I'll just talk about really cool stuff, at least really cool to me. And then we'll turn it over to you in a few minutes. All right, so we talked about you can take metric properties, properties of graphs, you can turn those into coarse equivalents, and you can try and talk about how those might be meaningful. You can try and prove that they represent certain properties that are respected or preserved or have some meaning under a quasi-isometry. Alternatively, you can talk about taking a graph and finding different ways to manipulate it in such a way that you are acting with a quasi-isometry. So I don't know how else to say that. Find ways to change a graph that doesn't break its quasi-isometric class, if you will. You're not creating anything that's meaningful in the sense of not equivalent under quasi-isometry. Another interesting thing you can try and do is to look at graphs. Graphs are neat. We have a lot of different, let's take a 12:30 moment to appreciate. Graphs are neat. Okay, so graphs have been studied for a long time by a lot of very smart people. And something these very smart people have done is break graphs up into families, classes. We can talk about great big strings of graphs that all fit under one particular title or another. One of those that we talked about earlier, Molly introduced actually, was planar graphs. Graphs are planar if you can draw them on the plane without crossing your edges. Planar graphs are complicated, and we don't dare begin to approach them here. So let's take something really simple. Trees. Trees are graphs that do not have any cycles inside of them. What does that mean? Well, I have a vertex, I can go out from that vertex, I can keep going out, keep splitting my paths apart, but they can never join together again. I can't have something like this because that is a cycle, and I said no cycles. But think back to the first 5 minutes of this talk. This is probably okay. Why? It's a little cycle. Oh, come on, just one little cycle never hurt anybody. So let's say it's probably okay to have a little tiny cycle. What's the theme of this talk? No big cycles. What do we mean by big? Well, put a scale on it, and then I'll tell you what we mean by big. But a tree is a graph that has no cycles. An interesting question to ask might be, when is a graph maybe not a tree, but maybe close enough? When can I quasi-isometrically morph a graph into a tree? That's a really cool question. And I don't think... Do you want to see the proof, or do you want me to talk about other interesting questions? You want the proof? Okay, then I will finish by attempting to prove a quick idea for when a graph is versus when a graph isn't quasi-isometric to a tree. Something that mathematicians call a classification. Yes. We'll take our last bit of this talk to classify when a graph is versus isn't quasi-isometric to a tree. So, trees are about cycles, so let's start with cycles. What is a cycle in a graph? Well, first level analysis, I think I gave you the definition earlier of a cycle is a path that starts and ends at the same point. We're going to change that definition a little bit to make it easier to coarsen. We're going to say that a cycle is two paths that start at the same point, end at the same point, and have no other shared points. So, translating that into a metric condition, a cycle is two paths, and let's call them P1, which is going to be equal to x1, x2, x3. These are vertices, the edges between them as well, all the way up to some xn. And let's call it P2, which is going to be some y1, y2, y3, up to some possibly different ym. And then they have to start and end at the same vertices. So that means that x1, and we're doing this as, I could say x1 equals y1, but we're playing with metric conditions, right? So let's be fancy and go distance x1 to y1 is 0, and distance from xn to ym is 0. Okay, they start and end at the same point. Now, they can have no other common points. What does that mean? Well, that means that for let's say I not equal to 1 or n, then the distance from xi to, for I not 1 and I not n, and then let's pick a j not 1 and a j not m, the distance from xi to yi is greater than 1. Greater than 0 or greater than or equal to 1. How about that? Okay, I claim this is a metric condition that classifies or that talks about what is a cycle in a graph. They start at the same point, they end at the same point, nowhere in between are they the same. And then paths have the implicit going from this to this is distance 1, from this to this is distance 1, from this to this is distance 1. We want to coarsen that. We're going to coarsen this definition by, well, we still want probably some kind of a connection at the ends, so let's not touch that condition. But let's play with this one. Here we say the distance is bigger than 1. What have we done typically with distances bigger than 1? If we think back to, well, connected is basically the only example we did. Distance is 1. We generally just turn that into a distance m. So we're going to make it the same idea. We want the distance between anything on the one path and anything on the other path to not only be not the same, but we want it to be big. Now we're going to have to tweak these a little bit to make that work. Why? Well, because they have to start at the same point. And if they start at the same point, then the first point along each path is still going to be pretty close to the starting. And so by the no detours rule, triangle inequality, they're going to be pretty close. So let's say instead of j not equal to 1 and I not equal to 1, let's say j and I both have to be more than, how about m? And instead of this, let's say less than n minus m and m. Oh no, I used m twice. This is dangerous. I have two m's that both mean different things.
Just make one bigger.
Yeah.
Yeah.
Add another.
Let's just do. Okay, I think that fixes it. Pointy m. M is the coarsest letter. Okay. Okay, so there's an idea for a cycle. Now for a tree, what do you think? Our question is, a graph should be a tree if it doesn't have any cycles. So a graph should be coarsely a tree if what? Well, if this is the rough notion for a coarse cycle, it should probably be a graph is coarsely a tree if it doesn't have anything that's coarsely a cycle. Coarsely means we have to fix a scale. So we've done that. M is our scale. Something is going to be coarsely a tree if there is a scale at which it doesn't have big cycles. What that means, think back very beginning, we're looking at graphs from far away. So take a graph, start looking at it from farther and farther and farther and farther away. If at some point these cycles disappear, that's what we want to call a coarse tree. And that translates in this condition to if there's an M big enough that there are no M coarse or M fat cycles, then we're going to be looking at a quasi-tree. Okay. We want to use this as a characterization for quasi-trees. That means we're going to use an if and only if statement. Something is a quasi-tree if it doesn't have fat cycles, if it doesn't have big cycles for some big, and something is not a quasi-tree if it does have big cycles. One of these is much easier than, well, neither of these is too difficult, but one of these is really easy. And the really easy one is the if you have really big cycles. I mean, that is intuitive, right? If you have really big cycles, no matter how far away you zoom, you still have cycles, you shouldn't be close to a tree. But let's just quickly make that an argument. So if for all m, this should be pointy m, we can find we have, let's call it m scale cycles, then we are not quasi-isometric to a tree. Okay, how do I want to prove this? Well, I want to prove it using the earlier arguments that we made these arguments about the images of connected sets have to be connected, and then the neighborhoods of the images. The images of connected sets have to be coarsely connected, and then the coarse images of connected sets have to be connected. So let's use that. I think we can use that. Is everybody got that fresh enough in their mind, or do you think we should jump back and put that? I think we'll be fine. So let's assume that we are quasi-isometric to a tree. That means we have a quasi-isometry that takes our graph to something that has no cycles. Now, let's assume to a contradiction that we're doing this with something that has really, really big cycles. What we want to do is we want to show that the image of this cycle has to still be fairly close. A big cycle is going to imply that its image contains a cycle. So take a really big cycle. This is a connected set. Its image is going to be coarsely connected, so its coarse image is going to be connected. Now, this cycle is really big, and one of the other things we have there is connected things go to connected things. We can also talk about disjoint things going to disjoint things. I skipped that proof because I did, but I'm going to use it anyway. So I have my cycle is connected. Its image is going to be coarsely connected. However, inside I have this path with things that are really far away from each other going on. Those can't come too close together. I have two paths between 2 points, and at a certain point, these paths are really far away from each other. That means when I do my quasi-isometry, they can't come too close together. So they still have to have at least some distance between them. And they still have to start and end at the same point. That's a cycle. I can't do that. Is everybody okay with this? Okay. Other direction. More interesting, I think. But I think a lot of things. And some of them are even true. Only some. Okay, other direction. We want to take a graph that has no cycles, no big cycles, and we want to show that it is roughly equivalent to a tree. So here's how we're going to do that. We're going to grab a point inside of this graph, right there, and we're going to break it up into we're going to break our graph up into big rings around it. Call these, we're going to layer the graph. And these layers are going to be defined using distances. This is going to be everything within, let's say m is the scale at which our cycles disappear. These layers are going to be defined to be distance m. So this first bubble is everything that is distance m from, let's call this point x0.
Would that be spiky M then?
This would be spiky m. Okay, so that's everything that is spiky m from x0. Yeah, okay. Then this next ring, this is going to be everything that is 2 spiky m from x0. And then the next one is going to be 3, and on and on and on and on. Now, my goal is I want to quasi-isometrically manipulate this graph into a tree. We had a couple of quick little things we did earlier about what I can and can't do quasi-isometrically manipulating things. And if you remember, one of those that we actually did and spent a little bit of time on was contracting sets that are uniformly bounded. So I'm going to take this graph, I'm going to find a bunch of uniformly bounded sets, and then I'm going to contract those and claim that this gives me a tree. My uniformly bounded sets are going to be connected, not necessarily, they're going to be M connected, so coarsely connected chunks inside of these rings, inside of these layers. We'll call these coarsely connected chunks, call it a block. So we have layers. Inside of each layer, we have these blocks that are coarsely connected. And I'm going to contract each block down to a point, and that's going to be my graph in the end. I need to prove that when I do this, two things. I need to prove first, these blocks are bounded. This isn't too hard. Assume to a contradiction that you have blocks as big as you could possibly want them. That means I can go way out here, and somewhere I have a huge block, really big. Inside this really big block, well, it's unbounded, so there's a path that is really, really long. How long? As long as you possibly could ever want it to be. And now I'm going to use this. Remember, these layers were built with uniform distances coming from down here. So I'm going to drop straight down to where I started. And these paths have distance, well, I don't know, but they're moving pretty much straight down towards this point. And at some point, they meet. Maybe they meet right here. Maybe they meet sooner. Maybe they meet right here. They meet at some point. But they can't meet too quickly because they started far away and they have to travel that whole distance before they can meet. They do have to eventually meet because they're both the same distance from this point and I'm moving towards this point. So there's a big cycle. If I have a big cycle, if I have a block that is big, I have a big cycle. And so for some, we are very loosely going to interpret what it means to be big, and it's going to mean like 4 different things in the next 5 minutes. Okay? Okay. If I have a big block, then I have a big cycle. So since I have no big cycles, that's our assumption, I have no big blocks. Now, since I have no big blocks, that means that I can take each block and quasi-isometry, contract it down to a single point. What remains to argue is that when I contract each block down to a point, the graph produced is a tree. So let's once again assume to a contradiction. I told you it was my favorite kind of proof. Let's once again assume to a contradiction that the graph produced is not a tree. That means that out there somewhere, I have a cycle. That cycle is going to look something like that. Why is it going to look something like that with a layer cutting through it like this and a layer cutting through it like this? very roughly, it's going to look something like that because inside of each block, inside of each layer, these blocks are bounded. And I pinch it down to a point, but I need a cycle. If they meet, so we're coming out from the root with everything. Eventually, there's a cycle. That means there is a point where it splits, and some point later where it connects. So this is like the simplest possible way to do that. There are some more complicated ones, but we won't worry about that. This is enough. If I have something that looks like this, they're connected down here, they're different up here, and then they're connected again up here. Well, they're connected up here. That means that their preimages are connected. They're different down here, and they're in the same layer. So that means their preimages are not just disjoint from each other, but they're coarsely disjoint from each other. They're M-disjoint from each other. And they're connected again down there. That's a big cycle, isn't it? That's exactly what we mean by a big cycle. They start at the same point, they get really far away from each other, and then they end at the same point. That's a big cycle. That's that. Everybody kind of okay with what's going on here? Questions, comments, or concerns? Aside from the fact that I clearly need a nap. And I'm not going to get one because we are not, I mean, what time is it? Midnight? We got 9 more hours. Okay. It's 1 o'clock. We have 8 more hours. Okay. So, going once, going twice. Hit me to the last couple of slides here. Go again. We did that already. Oh, here's a fun fact. Trees, they're one of the like very, 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 very few classes of graphs we can do this with. If you make it anything even slightly more complicated, we have no idea what we're doing. It's tough. Okay, give me another one. Another fun question. I have a neat answer, but we won't talk about it. I think we're at a good enough place to just call it because it's that time. We've done our 3 hours. Alec, your turn. All right, yay. Say what now?
Having 9 more hours and 3 more hours? What happened to time?
We've done our 3 hours.
Oh, got it. Okay.
Okay.